Okay, so today I'm going to switch what we're talking about today. Today we'll do the non-maximum suppression stuff, and then Wednesday we'll do the perspective transform. So in the, I don't have the, let me pull up the project description. Okay, so like when you've done the face detection, that there were a lot of times you would get many different detections, and you get these overlapping boxes. Okay, and it all depends. I'll show you. It's interesting. I'll give you two examples of how I've run this project, and I get different results. But this is what we call a heat map. And essentially what it does is, for every one of the rectangles, any pixel that's inside of one of the rectangles will be incremented. So if a pixel falls into two overlapping rectangles, then that part of that image that's overlapping will have a count of 2. So basically you want to add a value for every pixel's value will be how many detection rectangles does it fall in. Okay? And so this heat map, you can see I got a lot of detections. Over here is this, maybe I can, let's see, where is the image? Here's image. Over here, here's all that pile of all those cones over there. But even things up here, the wall up here sort of got detected a lot of cones, even over here did, and a lot of things around, like even right here is kind of interesting. This part on the floor got a lot of detections. Now part of that is because, at least the way when I did my training images for cones and not cones, I only selected things that were inside the field. So I didn't choose things that were outside the field because I was only training on things that were inside. So this is again a limitation to machine learning in general, is that your system's only going to be good as the information you train it on. And if you only train it on one type of situation, it's not going to be able to generalize necessarily to another type of situation. Okay, so eventually what you're going to do is you're going to filter away everything that's not inside the field anyway. Okay, so I didn't have to worry about any of the things that were out here because I only picked the stuff that was in the part of the image that is in the field. And that's called selecting a region of interest, where you identify some place in the picture where you're looking for what you're trying to find. So for example, if you're trying to find lane boundaries in a car, okay? If your camera is pointing, parallel to the ground out of the car, everything above the top, in the top half of the image, will be above the horizon, assuming you're on flat. So there's no point in ever looking for anything above the horizon. Okay, so you can do that. If you already know sort of where the road was the last time you detected, maybe you can throw away some things on the side. So that's a trick that we do a lot of times in image processing. If you know there's portions of the image that can't possibly contain what you're looking for, you just throw them away to make your problem simpler. Okay, so that's part of what I've done when I implemented this, and we'll talk more about that when we get to the perspective transform. That'll be really easy to do. You could, if you harken back to 2610, and when you clicked on the 4 corners for those folders and you've got away everything in the image, we're going to actually find an easier way to do that, because we're going to transform this into a square domain, because when you look straight down on top of the field, it's a 12-foot by 12-foot square. Okay, so it'll be a little easier than what we did in 2610. So you can see in here, most of the place, most everything here is actually, there does seem to be a cone. That guy is this one here. Now this piece right here, this looks like a false negative. That piece right there is this cone, I think. Okay, and the piece under it seems to be a false negative. Just like that one right there is probably this cone, and to its left there's a false negative. Okay, now in general the false negatives are weaker, okay, and so the color, the more yellow there is in that picture, the higher the count of pixels there were that were overlapping. Okay, so especially, depending on how you do your sliding window search, especially if your sliding window search only moves over every, if it moves over every pixel, you're going to get lots of overlapping things over top of, where there actually is a cone. So this heat map, the number of things you're going to get here is going to depend on how many sliding windows you use. I think in mine, I skipped every so many pixels, and I think that's why it gets that sort of checkerboard picture idea, is because it's skipping some, I think, but I'm not sure. I was always a little curious why I got that checkerboard, okay? But I think that's probably why. So, how many steps you make in your sliding window search is going to determine the number of how large the numbers can be in this heat map, okay? So when I developed this, my solution for this, anything that had a heat map value less than or equal to 2, I threw away. So if there were if there was 1 by itself or 2 overlaps, I threw it away. Okay, so for example, this guy right here got thrown away. There's right above the cursor there is a 1, and then right there, that's 2. So that one got thrown away. Now I think that might actually have been a cone. I think that may be this cone here. So that one actually did get thrown away. It was actually a detection, but it got filtered away in the heat map. Okay, and the main reason for using the heat map is to get rid of the false positives so that you don't have false positives. And obviously, it did get rid of this guy right here. Okay. Although there was one little streak that got kept. You see that one little streak? Sometimes there's these little streaks, okay?
I think that little streak is just the bottom of the cone.
It may be, but once you do the non-maximum suppression, it's just a little bit of a streak. You're right, I think it is that one right there is originally a cone. That one there that was this piece down here, which was a non-cone, okay? And so once I filtered out my heat map, then I did get some of these little bits. And I also went ahead and say, well, if the size of what I have left is very small, or if the size of what I have is very large, like this one, okay, that's all this mass of sort of these 2 cones and all the red ones. Okay, so you can throw away things if my detection is very small or my detection is very big, much larger or smaller than what I would expect my cone to be, I can throw them away too. Okay, and so in the end, once I did the non-maximum suppression on that, then I went ahead and built bounding boxes. Okay, and one of the nice things is once you filter that out, there's a command called label. So let's see, this image right here is that one these 2 are the same, okay? And then there's this labels function that will find continuous regions in the heat map, okay? And I don't remember, it's part of scikit-learn, right? Yeah, scikit ND image measurements. So there's this label. So you pass to it the heat map, which is a matrix, well, a 2D NumPy array with integer values in it. And it will find where are the things that are overlapping. Okay? And so it will go from this image here to this image here. And each region gets a different color. And labels will return a number. It'll tell you which pixels belong to which numbers for these labels. So that's really nice. Once you have the heat map, you don't have to do any work to get it to glob together into different regions. Okay. So this little guy ended up to be a region, and that one ended up to be a region. And then one of the things I did is I filtered away anything that is if a region is too small, I get rid of it, or if it's too big, I get rid of it. Okay. Now, to make the bounding box, there's several different ways you can do that. One relatively common way is to take this blob and find what is the maximum and minimum X and Y positions, and then just inscribe that inside a rectangle. Okay? And then that can be your bounding box for that region. Okay? Some of the newer techniques are what's called semantic segmentation, where basically your classifier will output an image, and in that image it'll say whether the pixel is what you're looking for or not. So in those ones, a lot of times they'll leave sort of this contour here, that shows which pixels are part of it and which pixels are not. But in this situation, we have no identification for sure whether that pixel is actually part of it. We just know that that was high in the heat map. Okay, so I recommend just drawing a box around, finding the maximum, minimum in each one of the labels, and that's pretty easy with this guy here because it'll return. It returns labels. I think it's a, if I remember right, it's a tuple, and one of the elements, the 0th thing in the tuple, is the image itself. The image, the 2D array with the integers in it that say which the number of the label is, and then the other one says like how many labels there are and what labels. There's some other things in that that tuple, and you can check that out. All right, so once you get that, okay, here's where I have the labels. Oh, come on. And then I want my other one is this guy, and here's the bounding boxes. So I got all my labels, and then I drew bounding boxes around them, and you can see I had to ignore any ones that had the bounding boxes that were too small or that were too big. Okay, and so this still includes some things that might be outside of the field, but we'll filter that out when we get to the perspective transform part. Okay, now one of the interesting things I found is that when I had trained mine, I had trained it with a linear support vector machine classifier. So it didn't use any of those kernels, and it only had hyperplanes in the actual feature space. Okay, I realized that after I had done. Actually, I realized that just yesterday or the other day. Okay, and so all of these results come from not using any kernels. Okay, and I actually have a poorer classifier because of that. Okay, and I'm hiding the code in here so you can't see everything, but let me run this one. Okay, and here it's doing the sliding window search, and I have it put out every time it goes through a row in here, and I think there's 900 rows or something like that in this image. And so once it gets up to 900 something, then it'll be done, and it'll go back over the write the images. So this is what I'm talking about, that this process has to take no more than a minute on my machine. Okay. All right, so it's done, and now what we need to do is I need to click in the image to tell it where the corners of the field are. So I have a G input in there. So I click there, you see it got a real red mark. You'll click here, you click in the other corner, and then you'll click in this corner, and then it goes ahead and does all of the images. And what you'll find now is that when I did the support vector machine not with the linear classifier, it did a whole lot better. Okay, so actually with the heat map, this is, let's see, where's the original heat map? Here's the original heat maps. Okay, and I actually, in this case, it did so well of predicting them that all of the things that it detected were all actually cones. Okay, it actually got, even those two in the back, these two in the back here, it got all of them that it had at all in there were actually cones. This guy over here is this one. That's a little bit big. There's a little bit of a false negative sort of on its side there, but it was overlapping. It's going to end up with a little bit bigger of here, of the bounding box ends up bigger, but they're all actually cones. Okay, so depending on how you set up your training with what are your what are your cone and what are your non-cone images, whether you use the naive Bayes, I use the SVM, whether you use naive Bayes, which SVM you use, because there's several of them, okay? In this case, it turns out that the heat map, I didn't get a lot of false positives, okay? And that's probably because it did pretty well in, I'm sorry, it didn't get any false negatives. It did pretty well because this image was the training images, okay? Now, when I did my test image, which I'm not going to do because I'm not going to show you what the test image is, okay? When I did the test image, I did get one false positive, okay? Both with the linear one and with this one here. So you may, you know, if you use the heat map, you still may be able to get rid of some of these false negatives, okay?
The same false on both sides?
It was the same one on both. Okay, so and so that's what I came up with. You needed to get at least 5 detections and at most 1 false negative, because I think I got 7 or 8 even with the linear SVM. I got 6 or 7 or so, and then I had 1 false negative. So that's where I set the bar for that. Okay, so you know this is a really good assignment in the sense that you're going to have to do everything. Okay, where you're going to be creating your data. And really, in the end, that's what all of these machine learning are all built on, the data. And if you don't have good data and lots of it, okay, generally you can't do anything very powerful. Okay, in this problem, we're trying to find yellow cones. That's pretty easy. I mean, really, you could probably do a regular standard image processing technique just looking for yellow in here, and that would probably be better maybe even than doing a machine learning. But you know, most problems are not looking for yellow things and there's no other yellow around, okay? Or even a cone shape that's nice, you know, here it's just changing in its size a little bit, where, you know, finding it. So in a more complicated problem, getting lots of data is tricky. Okay, but that's actually one of the reasons why machine learning's experiencing a renaissance now, is because there's so much data available on the internet, and there's so many data sets that people have already built on the internet. And so, you know, that's part of why, you know, I've even gotten excited about machine learning again, because, you know, before I really felt, you know, the human did everything. The human went in and collected all the data, found all the data, labeled all the data, came up with all these fancy features, and then the machine learning algorithm just simply found the relationship between, you know, what you gave it and what you told it to do. And it didn't do all that much on its own, okay? But our last assignment, our last project is going to really show us how the newest things with the convolutional neural nets are really neat. Okay. All right. So, like I said, you're going to need to, you know, collect your data. So, I think the way I did this, if I remember right, is I would click on one corner and click on another corner. I do a G input like we've had in MATLAB. Of course, Matplotlib does the same thing. G input works basically exactly the same. Where I would click in the 2 corners, and then I would resize that image to a particular size. And then I would always train off of that size. So even if I picked one of these guys and clicked on it, and then I would resize the image to that size, and then I would you know, use that as my training data. And so then I saved, you know, here's all my cones, here are my not cones, and I didn't use a ton actually. I mean, I did every cone in the image I did, and then I don't know if I did, you know, maybe the same amount or a few more non-cones in there, trying to get, you know, all the different things that were not cones. So, you know, that's what the way I worked it out. Okay. So now that you guys have started looking at this, anybody have any questions? You getting anywhere? Yeah.
Would it be a good idea to do the same thing with other images we found for the training set?
Right, so it would be a good idea to take more pictures with cones and non-cones. You're welcome to, if you want to, be taking pictures of them in other situations than in the field. I mean, that would be good, and that would help you to be able to solve more general problems, but it's probably not worth your time to spend a lot of effort getting things that are not in that field, because in the end that's what we're going to be looking at. Okay, so probably, you know, going, if you can get into, you know, go into into 118 sometime and put some cones around and take extra pictures. Absolutely, take them from different angles, from different places. That would be good.
I found images on Google image search with other VEX courses.
Gotcha.
With the VEX cones.
Yes, I think that's fine too. Especially if their cones are sitting in the field that looks basically like this.
After class, I'll show you some of the pictures.
Yeah, no, I think that's great. But like I said before, you want to be a little bit careful about the size of them. So if you click in them and you get a cone, you want to reshape it to be the same size so that you're always having the same size images.
Another question about the cones as well. In your test image, is it only going to be yellow cones, or are you not going to divulge that information?
It will be similar to the things that are in the training image.
Okay, because I was just thinking it would give false positives if you're just looking for like angled edges with the red and blue cones if you stack the yellow cones on.
Right.
So
There are the red and the blue ones in the training image, and there's likely to be things, similar things in the test image than there are in the training. Okay? And so that's also why we have not just the hog features, but also the color histogram features. Because if you just used hog, you would more likely, that one might be interesting to do, is to limit your features to only the hog ones and see if you get the green, the red and the blue ones more frequently. So yeah, all the things that are in there are probably going to be in there in the test image too. I'm not going to suddenly throw in all this other crazy stuff, I just want to keep you honest that you don't, overfit everything to this one image, because it's very tempting. And like I said, a lot of researchers do that, where they'll, keep optimizing their algorithm and keep checking, how am I doing? Oh, then I need to fix something to make it better. That's normal. You want to, see what is working better, and then you keep trying, and what you don't realize is you have this, bias towards whatever you're using to evaluate it on, and then you may be just doing really well on that and not doing very well in general overall. Okay. So, other questions? People starting to look. Anybody look at this? Justin, you look at this at all yet?
No, I haven't
He's
even
not.
started
He's
yet.
not on top of it like he has been. Okay.
Been helping the lady friend move to California. She gets on a plane today, so life goes back to normal as of 2 o'clock.
I hear you. You gotta find a space for those things in your life too. So the heat maps, that's pretty easy to build. You start with make an array with zeros, and whenever your sliding window goes through, if you get a detection, then you just do a slice and say, from the beginning of the window to the end of the window in the row, from the beginning to the window and the end of the column, set that, take whatever those values are and add 1 to them. Increment those. It's really easy in NumPy. You can, increment all the places inside that window in just one line, which is really nice. And so as your sliding window goes across, you keep incrementing them, keep incrementing them, and then you can do something really easy with logical indexing. You do something like heat map less than 2, and then that's going to give you a NumPy array with bools in it, and then you can say make the heat map where the heat map is less than 2 equal to 0. Set those ones to 0, and then you've got this guy here, and then really nice, you just pass that to this label function and you got your labels. It's really handy. Okay. All right. So maybe we can get started. Maybe I can come around. We can start looking at some of the images or building training data or something. No other questions?
What size images did you use for your training data?
Let's see. For the training data, I don't know. I think I think something like one of these guys. I clicked on one of the mid-sized cones, and saw about how big that was, and that's what I decided to have for the size in my sliding window search. I only ever did one scale for my sliding window search, but even still, if you've got a smaller cone inside that window, I still was getting some hits on them being images even with the smaller cones. So I guess I sort of picked something in the middle of the size of the cones and used that and resized everything, the cones and the not cone, all to that size. And I don't think I was very careful when I did the cones and not cones. Like, I tried to get about the same aspect ratio, but I don't think I was very careful about that. One time when I went through it, I would just select the bottom left corner, and then I let it go and take whatever the size was.
Yeah.
I did that first, but I found it kept chopping off the cones, and it was hard to get it just the right thing. I guess I could have been fancy and had some sort of interactive preview of where the window would be before I clicked on G input, but I didn't get that fancy. But I think in the end I didn't do it that way, and I just went ahead and clicked, and I tried to keep the aspect ratio as close as it could, but then it resized it to the shape it was anyway, and it seemed to work okay. But those are all interesting questions of how do you easily create your data, and to see how it may or may not affect your performance in the end. Yeah.
I'm guessing we're going to need to cycle through all of our training images where we're going to be selecting what is a cone and what's not a cone, doing the G input for each image to build our training data.
Right. So I went off of just a single image. Okay, so I had my single image, and I would click in one corner, click in another corner, and then I would extract that piece off and save that as a JPEG. And so then I kept doing here's cone, here's cone, here's cone, here's cone, and it kept saving them and I named the files cone and then a number, and I just kept increasing the number. And so then if you had multiple files of images, you could just then click in the next image and then just have that cone and the next number, cone and the next number. And then when I was going to train, I just did a glob, find all of the images that start with cone, and then pull them in and then calculate their features and train, fit my classifier with that. Okay, so yeah, if you do different images, just copy them. And I would like you to do that to save those images so I can see, which ones, what did you use for cones and what did you use for not cones. That'd be really helpful for me to be able to evaluate things. I'm pretty sure, did I write that in the submission guidelines? Hopefully I did. Yeah, this, as well as the training images organized as in subfolders. Organized however you want. I think actually I had them all in one folder, but I had to have them have different names. But it doesn't matter. You organize them however you want. I'm sure you're not going to do it so complicated I can't see where your cones and where you're not cones. Surely that won't be too hard. Okay. So that'll take a little while to identify all of your data. So even in the end, I got this little guy. That one, this little detection. He was small, but not too small to get filtered away when I got rid of the big ones and got rid of the little ones. But also, let's see how many detections did I get in here? So 1, 2, 3.
Locations to print on the figure.
We'll talk about that on Wednesday, but first, the main idea is first we do a perspective transform, which makes you look straight. It brings it into here where you're looking straight down on the image. It's as if basically you assume everything in the image is on the ground, and then you move the pixels to where they would be if you were looking on top. So things that are tall get distorted, but things that are actually on the ground turn out to be very nicely done. And so then, so like this point here, this is a perfect diamond, and these things are perfect squares. The tiles are nice perfect squares. And so then, you know in the real world that this is a 12-foot by 12-foot field. So then you can just, do some proportions of where things are in there, and then you can get the distances.
I just meant how to actually display them.
How to display them. Okay. There's put text. It's an OpenCV command And I'll show you some of those details on Wednesday too. But yeah, there's a OpenCV command for put text. It's a bit cumbersome, but it works okay. So let's see. I mean, it even got, there's some of those ones in the back didn't get, well, let's see, how many you get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it got 16 of them. I don't know, what did I say was, how many did you need to get in the training image?
10.
10. So, you know, that got way more than 10. So that's, you know, should be able to get that many. But it's not perfect. You know, this guy was tall. You know, the bounding box was a bit tall. This guy was a bit wide. Let's see, what is the heat map look like? So, yeah. I mean, it's tricky because if you get rid of that, you have to get rid of anything that has a heat map value of 1. But if you do that, then you're going to drop 7 of your detections. So it's always this classic, you know, getting rid of false negatives and throwing away actual detections. It's one of those things you just never really get around, you know, unless, you know, if you can make a better and better classifier, that'll help. And again here, there's this guy is wide because there's this one guy, you know, on that very edge of that one box, it detected something it thought was the cone, and so it kept the stuff on the other side. So, I mean, in this one, if we got rid of everything that was 1s, it would probably be tighter bounding boxes. But, you know, that's not bad. Even still, this wide guy here, the center of the bounding box is still not all that far away from the center of the cone. So if you were going off of that, you're still going to get pretty close to it. So it's not terrible.
Why did it not get the one dead center?
This guy?
Yeah.
Yeah, I don't know.
Because that seems like it would probably be the strongest one in both the heat map and everything else.
It was not. It didn't show up at all in the heat map.
Weird.
And that's one of the things with machine learning is that you don't know why. It's this big black box of things that happen inside and you don't really know. And after Friday's lecture, I think many of you are like, I don't want to know what's happening inside the support vector machine.
Turn the crank, magic comes out.
Right. You know, and what's interesting is that machine learning is starting to become a thing where where you can be a technician almost and do it. You know, you don't have to necessarily understand all of the details. You just need to know how to use the tools. Rather than, you know, that's the classic difference between an engineering technology program and an engineering program. Engineering technology, they learn how to use existing tools in the best possible way. And engineers learn how to develop new tools. You know, so you guys are, you know, I sort of teach this class sort of straddling those two worlds. You know, I want you to understand how they actually work and how you might be able to develop new ones, but we're focusing mostly on how to use them. Okay? So, and that's one of the interesting things. There's a lot of, like, training programs for coding where, you know, there's like these, you know, like Udacity or whatever, but there's even like nonprofits where they do like training camps or training certificates for coding. And then like, you don't need to learn calculus and all this other stuff and all these fancy things. You know, you just need to learn how to code. You know, and you become like a coding technician. Yeah, you know how to write code and work the software, but you don't know the ins and outs. Maybe you don't know all the stuff about data structures and the theories on queues and stacks and all this stuff, but you know how to use it. You know, so we're sort of entering that era now with machine learning where, you know, you can just know enough about the stuff to use them, but maybe weird things will crop up and you're not quite sure why, you know, if you don't have some of the understanding deeper in. Okay? All right, so why don't we pause it